Are we okay on the camera?
Yeah, it's on.
Great. Okay, without more ado then, Colin McLarty, second talk, and the subject, as you can see, why is so much category theory constructive?
There is, any way you look at it, there are surprising, there are unexpected links to constructivism and category theory. Saunders McLean had no interest in constructivism that I know of, and positive skepticism about Brouwer. Bill, I mean, you're interested in lots of applications, but I think not really constructivism per se.
No, I'm also skeptical.
Yeah. I've lately, part of the
This claim that constructivism doesn't exist.
I would agree. My historical work on Eminetta has me studying Paul Gordon, who's supposed to have been a constructivist. Gordon was absolutely uninterested in constructivist principles. He was interested in actually finding answers to questions, which turns out to be a different thing, in fact. It's somehow related, but Gordon had an algorithm to take a binary form in any number of variables and produce a complete set of invariants for it. This algorithm was absolutely infeasible for 6 or more variables. No, it's 2 variables any degree, right? It was absolutely infeasible above degree 6. This pained him very much. He didn't care that he had an algorithm that in principle worked in all degrees. He couldn't do it. Different question. And I mean, I'm sure Saunders, especially during the war, had his interest in applied math, getting the problem solved. Different problem from constructivism. Topos logic. Now, actually, these slides were written for people who didn't know as much about the subject. So, Topos logic is formally unproblematic. It is, as I always like to discuss with audiences like this, you simply take Tarski's notion of model, interpret it in any category that will support the terms. That's, if the category is the Topos, that's Topos logic. There aren't choices being made here of shall we have excluded middle or not. Interpret logic in any topos. The types are objects, predicates are sub-objects, conjunction is intersection, quantifiers, well, adjuncts to substitution. They're just what they should be. Functions are arrows of the topos. It is a fact that in many toposes, using this interpretation, the axiom of choice is false, the law of excluded middle fails, and the double negation of a sentence does not imply that sentence. Again, this is not a choice we make. Hey, would it be nice to get by without double negation? It's simply, double negation simply doesn't hold when you interpret logic this way in many toposes. But this really does raise the question, why should toposes agree so closely with the logic that Brouwer and Heyting created? It is a puzzle to me. And I'm not going to give you the answer. I'm going to give some answers that I think are worth considering.
Why should Topos logic?
Yeah. Why should Topos logic agree so closely with this? We sometimes say that arithmetic in a topos is intuitionistic, higher order arithmetic. Well, as a historical point, it's worth knowing that there was no intuitionistic set theory before Topos theory. There wasn't an intuitionistic analysis before Topos theory. Trulster has this lovely volume in higher order intuitionistic arithmetic, in which he proposes, by my count, 438 named variant axiom systems for intuitionistic analysis. These have many unnamed variants in turn. There wasn't a thing called intuitionistic analysis. There is a thing called analysis in a topos, where you mean over in any topos you're talking about. But that said, it is true that second-order arithmetic in a topos looks an awful lot like second-order making arithmetic. It's just that we don't worry about what to do with comprehension, what to do with deduction. It's given by the topos.
It just struck me that it's quite analogous with what I was saying in the other meeting about the conceptual proof theory came before the constructive theory. In other words, when we had the meeting in Halifax where we sort of launched Topos theory, well, Nick Goodman came there and later collaborated with Mayo and had something which is, I think, now recognized as sort of the intuitionistic analysis.
Yeah.
Only happened with a little bit of conceptual push.
Yeah. You talk with logicians. This is less true now than it was 10 or 15 years ago. They would tell you that, of course, the intuitionistic set theorists knew that choice implied excluded middle all along.
Yeah.
Now, indeed, Brouwer had called choice a principle of omniscience, thereby bad because it would solve all questions. But, and then they'll tell you that Myhill and Goodman proved it independently of Topos theory. The first word in Myhill and Goodman's article is Diaconescu.
Right.
There is one bibliography entry in that article, Diaconescu.
There's a pattern here.
Hmm?
There's a pattern here.
Yeah, and it's not of Myhill and Goodman in any way concealing the first word is Diaconescu. But the collective memory of the set theorists.
Yeah. It's that all this stuff is, as it were, builds over the logic that.
Yeah. But it does remain that Topos logic is uncannily close to intuitionistic logic. And I got some possible reasons why. One answer would be, well, the resemblance is superficial. And to some extent, it is. But I think that's not enough of an answer. We would say it's rigged by selective attention. We've chosen which parts. To Brouwer's bitter disappointment, right? Because Brouwer is interested precisely in constructive content at the base, which we don't have here. Brouwer is not interested in formal rules of logic, which is where we do agree with the constructivist tradition. But we don't pay attention to that. We look at the parts that work. Here's a bit of a union of those two, that Topos theory is objectively tied to the motives for later intuitionistic logic, topology and process, not Brouwer's stated motives. Brouwer, was always very ambivalent about hiding formalizing his logic. He would sometimes attack it completely. He would sometimes say, oh, we're definitely going to do with this, it'll help expand the ideas.
Well, but just do you think, because it's rather, Brouwer so much work in topology, right?
Yeah.
So it's kind of hard to believe it's coincidence.
That's what I started with. But then you read his topological papers. I think they agree with what he called his intuitionism in the period of his dissertation, 1907. What I'm about to say would be banned from the world by Van Dalen. Van Dalen does not want to hear that there were any changes here. But in the dissertation, Brouwer says excluded middle is harmless. It just means if A, then A. He says double negation is harmless. He says what's harmful is paying attention to the logical inferences you use. For Brouwer, the goal is to not pay attention to the logical inferences, to just pay attention to the subject matter. Well, this is quite opposite to what he would later, when in his famous paper, The Splitting of Classical Concepts. There's a beautiful place where Brouwer proves his fundamental theorem that you have a continuous map, we would say, between triangulable spaces. The degree of that map at any point is invariant under small deformations of the map. This is going to be the key to all his results in topology. The degree is a homotopy invariant, we now say. And the way he proves it, he constructs four numbers, and he wants to show they're equal. He shows this one equals this, and this one equals this, and this one equals this. And then he says, now, suppose these two weren't equal. And he proceeds to draw a contradiction. If you think it through for a minute, you'll see this contradiction can only be gotten by using transitivity of equality. He has in no way circumvented transitivity of equality. But he has worded it this way. He's made an appeal to an utterly gratuitous proof by contradiction because he doesn't care whether he uses proof by contradiction. It's not an issue to him. And this is 1910, 1912. That's what goes on in his topology. His topology leads him away from logic. Yeah. He says he wants a language-free mathematics. And I would take that very seriously. I like what Huck says. I can only quote most of it in translation, but when I was a student studying topology, I heard of Brouwer's results, and they were just an illumination to me, these wonderful results. And then my teacher had me read Brouwer's papers. And here I'll try some German. Das war eine saure Arbeit. And it is. You take any of these topological papers, on a first glance through, as you're sizing it up, because they're short, you think, this is wonderful, this has to be right. And on a second careful reading, it falls completely apart. You can't see how anything is supposed to follow from anything else. And in my experience, and I take it Hobbes, you keep staring at this thing and meditating on it, and you never do learn the proof from the text, and yet you know the proof after a while. The ideas come together even though it's not from any statements in the text. And I think that's a true ideal of language-free mathematics. It's not my ideal. I'm not interested in writing language-free mathematics. But I think it's really fair to say he wrote a language-free mathematics at that time.
Maybe topology is better adapted than maybe topology is better adapted than all the subjects do.
Well, and especially those basic results in topology of manifolds that were so. A lot of the obstacle to proving them was that they were so intuitively obvious that you couldn't see why you needed to say anything. And yet he saw exactly what you did need to say.
But it's dangerous. You can prove the Poincare conjectures many times this way because it's obvious.
Yeah. So I think what happens is Brouwer comes up. He's this genius. He has a lot of secondhand Nietzsche from his friend. I've forgotten the friend's name now. He gives these student lectures on life, art, and mysticism at Delft, where it turns out that man is evil and woman is essentially no different from a lion, and and the whole secret to Holland is that we get killed a lot in storms. Which we deserve,
Yes. It's all in the atmosphere of that time. This is about 1908.
Yeah.
This is old Fraser and the vote.
Well, this is what comes from philosophers not reading enough bad books. Philosophers say, well, Nietzsche was some decades earlier. Bergson was writing, but I don't see any kinship to Bergson here. Well, no, it's a kinship to the bad books of the time. This was ordinary student skepticism, student nihilism. And he insists that this new mathematics it's just done wrong. He's clear at this time and will stay clear in his intuitionistic writings that the results of 19th century math are not wrong. They're good because they're in fact founded on intuition. But this idea that Hilbert has, that you can formalize logic, this idea that various people have that you can distinguish different infinite sets, these ideas have got to go. These are unintuitive and damaging, but he does not think that any of the substantial results of 19th century analysis are at risk, and he says so in 1914, that none of the substantial results of 19th century analysis are at risk. At that time, too, he still has these various intuitionistic and pre-intuitionistic precursors. By, I think it's 1938, he will declare that no one before him was ever an intuitionist. I mean, he really is hardening his view as he goes. So here
What is his attitude at that point? I know a bit of George's comment that he said in specifically.
I am sure he mentions him and likes him, but
nothing more systematic.
Yeah.
Sorry, when was the continuity theorem stated? I mean, I know nothing about it. Intuitionistic now.
Intuitionistic versions?
Yeah, of course.
Well, these things begin 1919, 1952.
I see.
And I don't know the details because I haven't.
Yeah. But I mean, you can't say then that the results of analysis will be preserved.
No.
At that point, I mean,
He's
it's
later going to throw out
okay.
results.
But that's 1920. Yeah, roughly.
But at this point, he actually tells us in 1912, I guess 1912, on formalism and intuitionism, that all those results are good because they're all founded on intuition.
Even those on Weierstrass and so on about, even the Weierstrass tradition.
Yeah, because this is just a philosophical mood he's got. It's not a program yet. And he declares that he's going to create a new intuitive mathematics. It doesn't say intuitionistic, but a new intuitive mathematics in his dissertation. 1912, Brouwer becomes a professor. This was unheard of in Holland. In Holland at this time, you normally became a professor when you were like 63 years old. This was a capstone of your career. Brouwer, 1912, so I've forgotten exactly when he was born, but roughly 30 years old.
1886, yes, but 32.
32, he becomes a professor. And what's he going to do? He decides he's got to live up to this promise. He's got to produce this intuitionistic mathematics he's been saying. And it's got to be different. How is it going to be different? So he's got to look for ways to make it different. And what I would suggest is that working in the background here on Brouwer and also on Hiding is we've got to make it different in some way that makes sense. And what they find is, well, how about if we look for logic that'll remain steady under some changes? these might be small changes on metric space. We won't say everything is either equal to 0 or not. How can we get by without that? These might be changes through time. What happens as we learn more? What changes as we learn more? I think, but this is without any clear idea of which it is. But these kinds of ideas are at work.
When did the creative subject get
That's already in the dissertation, and two oneness, yeah, and the mysteries of two oneness. But I say that
So, just remind me the year in which you became a professor, you said 1912?
1912.
He's 27.
27, actually. 27 years old.
1885, yes, remember 1885.
Yeah.
Yes, 27.
And he's made, from a history of math point of view, is an interesting but not surprising choice. If you want to be a great mathematician in Holland, don't take up Kroneker's theory of elliptic curves, because all the heavyweights in Germany work on that. Take up something where there is not a long tradition yet, because you're stuck in Holland with nobody wants to talk to and not a great library. So take up something new. So he takes up topology. So I think, to a large extent, this is Brouwer's, and more than Brouwer's, Heiding's rationalization. We're going to find something that makes some sense and isn't classical logic. And what we find is sort of invariant under various kinds of variation. I see I cut it out here, but it is going to be invariant in topological sheets, if you want to use that word now. It's going to be invariant in Kripke models. It's going to be invariant in monoid actions. That these are attempts to say what could be a more stable logic, because we want something that's not classical. Von Dalen's first volume of the Brouwer biography I've read. It's a fantastic piece of work. Fantastic historical research.
Which is that?
Von Dalen's first volume of the Brouwer biography.
Oh, yeah.
But throughout it all, he keeps saying how Brouwer took one more step towards the creation of this successful intuitionistic analysis, and one more step. I haven't read the second volume yet, but at some point he's going to have to say that Brouwer, in 1952, says, unfortunately, the fundamental theorem of analysis has not really been given a satisfactory proof. He does not create intuitionistic analysis. He says he has failed to create it at the end of his life. So at some point, Von Dalen's going to have to say, well, you know, in this successful creation of a subject, unfortunately, didn't happen. His proof of the fundamental theorem, always to the end of his life, depended on consider a statement and consider what would have led you to make it. This is the opposite of language-free mathematics. This is proof theory. And proof theory is the very thing that's supposed to be banned from intuitionism. And he needs it to prove his fundamental theorem in any way he can think of.
What is the fundamental theorem?
You know, some bar theorem or something. I don't remember.
Oh, I see.
You know? Yeah, I should, but... So I think the resemblance is sort of superficial, because the motives had to be superficial. This was a philosophic project that didn't have any mathematical content. And then Heiding, especially, now Heiding is a very honest and friendly person. He's honest enough to produce some actual mathematics and friendly enough to make it match Brouwer's statements. And there is a little bit of a strain there. But yes, it's a very close point of attention. We found, that is we, by which I mean Brouwer, and more especially Heiding, but also Kleene and Kolmogorov and lots of people who contributed to this, found a logic that made some sense and wasn't classical. It did not vindicate Brouwer's early statement that excluded middle is harmless, it's the same as A implies A. Well, we weren't going to get anything different from classical if we stayed with that. So I think there really is a historical process of making sense of Brouwer, and Topos theory makes better sense of those same things.
I think that there is a further issue, because that's, you mentioned actually that this Heiding's formalization, say, in a sense, goes, falls apart of Brouwer project. But on the other hand, I think that the Topos logic, if you see that not just just another model of formal system, but as kind of geometrical foundation or something around the topology, that may also connect in different
Yeah, that's the kind of thing I want to try to say. Yeah, Topos logic, in fact, continues a trend that's going on in 20th century thought, a trend that Heiding tried to take advantage of when he wants to make sense of Brouwer's pronouncements. So this incorporation of variation, actually, Heiding and Topos theory are incorporating the same kinds of variation. Astonishingly enough, why should topological variation and monoid action variation and trippy tree variation, why should these have so much logic in common? They do have, they're not identical logic in the three cases, but considerable. And this is why Heiding had to pay a selective attention to Brouwer's ideas, and is select ones that you can make some sense of. This is superficial from Brouwer's point of view, but it is tied to real mathematics, and that's why Heiding ends up with it. And at any rate, Topos theory has been a productive source of formal models for many aspects of intuitionist foundations. I mean, eco with the doing their own choice sequences. I mean, did you ever imagine Topos theory would explain choice sequences? Did the issue come up to you?
No.
Yeah. And yet, it's the tool he uses to prove new theorems on free choice sequences, controls to satisfaction. The other question is about general category theory. There are themes we associate with constructivism now. There is, as Bill's been discussing this week, there's a philosophical motive that constructivism should mean you start with stuff you can get your hands on and build from it. That's not a question here. But another aspect that's coming to it is to be identified is we're going to avoid excluded middle, we're going to avoid specifying instances for existence claims, we're going to avoid the axiom of choice. That these formal issues, and a huge amount of general category theory does avoid all those things. And why is that? On the one hand, of course, we can simply declare we're going to avoid those things. We could do general category theory, having declared that we won't use axiom of choice and won't use excluded middle. That's just obvious. But so often we naturally avoid those things. I'm not sure if I can quote the exercises correctly from Bowden, but the Bowden Summer School on Category Theory, there was an exam at the end. And one of the questions was, draw the diagram and from the usual considerations derive the usual conclusion. And another one is, prove that all diagrams commute.
We don't just ignore these things, we actually measure the extent to which they fail.
Yeah.
People want to talk about that.
Yeah.
People have explained this. Andreas Boss, for example,
Yeah.
specifically shown that that's what control logic is doing, is measuring the failure of these.
Yeah. That exercise proves that all diagrams commute is a nice joke about MacLane's coherence theorems. But MacLane does show that all the diagrams that you would wish to commute in these situations do commute. Not that all diagrams commute, but that all, and this is, I think, it was my experience, I think it's a lot of people's experience, reading categories for the working mathematician. You come to an exercise, and think, in this situation, show that such and so holds. Well, such and so holds for the only reason it possibly could. You simply look at the data, you put them together the only way they fit, and you draw one arrow whose domain and codomain are the functors on one side and you wanted it on the other, you take its adjoint, and that is in fact your answer. The only, if the problem calls for you to construct an arrow, the only arrow you can define in terms of the data is the arrow you were to construct. And there is an arrow you can uniquely define from the data, over and over.
August MacLane was lecturing in Zurich, I don't know, in German, of course. His way of dealing with the uncertainty about gender was just to say it even louder. Anyway, there was this Swiss mathematician there who, at about 3/4 of the way through the lecture, he got up and left in disgust and saying, only trivialities can be expressed by simulated diagrams. So I ended up giving the definition of natural number object.
Yeah.
These are all triviality, and that's all you can do with community diagrams. So.
Yeah.
But I think that's sort of a similar response. I mean, all diagrams communicate that's what you perceive.
Yes.
If you're not an expert, you perceive that's what people are doing.
Yeah. Yeah, and I think, to me, that's one of Peter Fry's main contributions to the subject, is the statement that the point of category theory is to make what ought to be trivial evidently trivial.
I guess that was Eilenberg's basic original view. I mean,
Yeah.
whether you call it natural or trivial, it's the
Yeah.
same. It's so natural as it is.
Yeah.
So it's to be trivial.
Is that specific information,
Yeah.
as opposed to, is always expressed by wrong way maps.
Yeah.
Not the
Yes.
wrong way from the point of view.
Yes. Yes, it's the maps from the product. You give
Exactly.
information, maps to the product, where you know what those are. Yeah.
Yeah.
Yeah. Yeah. On this question, one possibility, category theory is about unique existence over and over again. We describe something as the unique this that does that. We expect proofs of unique existence in any part of classical mathematics to be constructively valid. They aren't always. That's not a meta theorem, but it's an expectation. Typically, unique existence is going to be intuitionistically valid. And of course, category theory is not actually about unique existence, it's about unique existence of isomorphism. But maybe that's close enough that it should be considered a major part of why so much of the subject is.
But it's at some point it is a problem, right? So from an intuitionist point of view, because we have to make some kind of specific choice when we have to have something concrete on our hands. I'm thinking defining functors up to isomorphism in adjoint. When you say, okay, I construct this adjoint via universal properties, so then you have to, okay, but now I need a concrete example to get it working, right? So.
Yeah, or in this foundational work I'm doing on cohomology, it's not good enough to say, I've pretty much told you how to define a cohomology functor. I've defined it uniquely, I showed you how to do each step. I need to show that it also exists. That this infinite sequence also exists. And I've got an up to isomorphism. And one approach would be to try to formalize things up to isomorphism, but that requires doing. Another approach is to say, I'll use global choice, but you have to take an approach, you know. Yeah, because it's not really unique existence, it's almost unique existence. And this is what Stachel was trying to get away from. He wants to talk about coordinatizing a situation, but he doesn't want to pick one coordinate system. So he says, consider, you know, the isomorphism class and all their automorphisms, which turns out not to really achieve anything, but it's a natural thought. I say, well, you know, I'll take them all up to isomorphism. Another possibility is that category theory is so general that nothing weaker than explicit constructions can work across the whole range of it. This is one of the brilliant things in categories for the working mathematician. Chapter by chapter, every construction is shown to be a terminal object in a suitable, fairly natural category. The claim that all terminal objects are isomorphic is, in a sense, every theorem in mathematics. Every theorem in mathematics can be put in that form by, often enough, a fairly natural construction. So, if theorems as trivial as that are going to have that kind of range of application, their proofs cannot depend on any intricate logic, because intricate logic would have to lose at least some of the cases. So so maybe another alternative is just so general that nothing weaker than explicit constructions can work across the whole range. Again, this can't quite be true because they aren't quite explicit constructions. They're typically explicit up to a choice. But I think there's something to this. Another possibility, you should say, well, look, it's simply not constructive. Category theory conceals the non-constructivity in its basic terms. This is certainly true. You can have a recursively presented category where composition is just not a recursive function. The whole thing is recursively presentable, arrows are recursively defined, identities are recursively recoverable, composition is not a recursive function. It's a tiny little exercise in how you make things not recursive to verify you can do that. The same way you prove anything isn't always recursive. so that we're just really not constructive in the epistemological sense of actually having data we can get our hands on. Category theory is too young yet to need non-constructive proofs. At what point do I have to retire this as a candidate? I began studying this in 1972. Category theory is substantially younger in 1972. And it must be said, and you can verify this by looking at things like the Category Cafe, we do get more and more non-constructive proofs in the higher ends of category theory as we go along. Sure. Or look at these things on homotopy cardinals, which I haven't really dug into, but ask about those people. Oh, I went with 4 there. Yeah. Or maybe it's that. So this is, to me, I mean, I'm not going to propose an answer here. I'm going to say the phenomenon really deserves attention. Topos logic is too much like Heiding's and Troelster's logic to just let it go and say, well, it just happened. I think it's worth trying to explain, and here I'm actually offering one explanation that Heiding's and Troelster's logic was designed to make some kind of sense in a situation that did not constrain what kind of sense it would make. And so it got more or less unconsciously tagged to stability under definition, stability under process, it got unconsciously tagged to these things, which then are then objectified in Topos for other reasons, and that's why it agrees. And on the constructivity of category theory, the sort of constructive nature of it, the fact that over and over again in categories for the working mathematician, like I say, to do an exercise, the point of the exercise is to understand what it's asking for. Because once you've understood what it's asking for, the answer is the first thing that comes to your mind. Unlike analysis, they claim that all diagrams commute, I think registers another thing. Over and over again in all fields of category theory, the diagrams you're at all tempted to draw do commute. Not always, but surprisingly often. Contrast just ordinary analysis in 3 variables, 3 real variables, over and over again. Formulas that you ardently wish would be true are not. But in category theory, every diagram you're tempted to draw, well, not every, but over and over again, all the ones you're tempted to draw do commute.
Under certain conditions, right? That's important.
Well, but I mean, the conditions that tempted you to draw it.
It's like you write equation,
I'm not
and
sure it's good.
under certain conditions, your equality is true, so another condition is false.
What?
Maybe not very
Yeah.
Right, I don't know.
But I'm not sure good for this. Not sure good for this
Well,
specific
great
subject.
expression, I quote, with certain conditions, right?
Depends on what you want to do.
So now the condition, it's not equal. Diagram can be used under certain conditions.
Yeah, but often the conditions are given. You're doing an analysis problem, you know what functions you've got, you know what you're trying to construct.
No, you want to have deep.
And lots of the lots of things you would like to try are in fact
Doesn't
bad
sound very
shortcuts.
deep.
You know what function you're trying to prove continuous, and you're going to do that by constructing the right approximations. And over again, the approximations you try fail completely. There's some insight that's needed to get the right approximations. This doesn't happen as much in category theory. If you want the internal hum, I want to take functions from the function object from B to A and the function object from A to B and then from B to C, and I want to compose to get the composite functions from A to C. You transpose, you bring that A over here, you write down the only arrow that you could possibly write from A across B to the A, across C to the B. There's only one. You write it down. Its adjoint is the internal composition. Completely unlike analysis, where you can cast around, or at least I can cast around all afternoon for the correct approximation and never find it.
Isn't there a connection here with what Bernardus was talking about yesterday afternoon when he was saying that people are asking the candidates for fundamental theorem of category theory, and what they come up with is not actually a theorem, but it's what he christened the basic Cowan business. It's just, it's obviously from, especially from Cowan's work, from You want to so naturally there to see how one should fill in diagrams.
Yeah, you see that.
In a way that is quite different from what happens in analysis.
Yeah. The only grammatically tenable candidate for a solution is the solution, very often in categorical situations, completely unlike analysis.
So by grammatically one would say diagrammatically.
Basically, I mean, the domains and codomains are right. Once the domains and codomains are right, the arrows are right, which is obviously not a metaphor, but it's a conspiracy.
Isn't it fair to say that non-constructivity enters as long as we start dealing with size issues? The main example being Freud's proof, small categories, complete lattice. And then there is more problem, kind of.
Yeah.
Results like those of Atomic and Trukova, etc., with existence of left-hand joints for accessory.
And I like that in
That depend
relation.
on large cardinals, etc.
I like that in relation to the stuff I'm doing on cohomology, because in the stuff on cohomology, nominally large categories enter in. But one of the reasons people feel they can't have needed to is that you don't get non-constructivity in the more advanced results. The proofs of the advanced results are near tautologies. And this is part of, at least for me, why you feel like it can't have needed inaccessible cardinals. But the ones that do are the ones that also have non-constructive steps. Yeah, that could be a valuable way of looking at it. Yeah. So those are just thoughts I had on the subject.
I thought that was only one of the questions.
Well, thanks very much, Colin. Plenty of time for discussion.
You know that I gave a much more precise answer to the question than you said. Well, namely, Brouwer had this idea of the subject. So the advance of subjective knowledge in some form. So this advance, the subjective motion is motion.
Yeah.
And essentially, that motion is complex enough already to reject Luhmann logic, even to reject Haydn logic that's truncated, by saying the 10th boundary operator is.
Yeah.
So Haydn logic is entirely justified, so to speak, by this one kind of, very specific kind of motion. And on the other hand, in Topos theory, we deal with much more general kinds of motion, but therefore, because they're motion, means you just look at the definition of the connectives in terms of going ahead and there exists overall. So, on the other hand, and then there are these source of completeness theorems for infinitary logic, with basically the idea that a topos can be covered by a localic topos in a way that preserves the logic. So the logic itself really is just the logic of motion. And when I say localic, you can go much further than that. You can find a zero-dimensional covering, things that are almost, whatever, I don't know, Brouwer gets to get more or less specific, the kind of time or potential time that the subject has to advance and so forth. If one looked at it closely, one might actually see that something almost compatible with his idea of potential time and the most extremely zero-dimensional type of covering that you can get would nearly coincide, which at the same time illustrates strongly that Topos theory is not logic. It is not reduced to logic because it's only. So with my axiomatic cohesion, I show even much weaker things. You show that interesting toposes are totally have sort of trivial logic, and you just look at it merely. So this, in some sense, these results have been leading to misconceptions because it definitely does not reduce to logic. It does not reduce to variation. That's what it is. Does not reduce to variation. Cohesiveness is, in some sense, may include variation. And conversely, variation may be used to sort of describe cohesion, but it's a description, it's not cohesion itself. So
Yeah.
the dialectical relation between cohesion and variation was not brought out clearly in the 70 papers, but I think if you just think about the logic variation part, that's where the
Yeah.
so just a sufficiently generic case of motion, i.e. Brouwer's advances in thinking, which of course we'll actually talk about, already suffices to account for almost all motion.
The only place I would modify that is that Brouwer's theory of the creative subject is, the best you can say for it is that it develops slowly over time. He doesn't have it at the beginning, he doesn't have it at the time when Hiding formalizes the logic, not in any developed way. And basically, I would say he never had it. Brouwer didn't have a theory. Brouwer wished to have a theory of the creative subject. He declared it would be the foundation, but he never had it.
Let's say they invented it, but they didn't yet discover it.
Yeah, yeah, and because they were inventing a fill-in for a theory that doesn't exist, they had the room to attach it to things that do make sense, like topological variation through time. Someone, I forget even where I heard this story. I wonder if it was from Lambeck, that somebody actually asked Brouwer at one time, what would happen, on your view, if suppose some mathematician is working on some subject and as a creative subject they prove a theorem, and some other mathematician as a creative subject proves the negation of that theorem? I mean, which is presumably the reason we don't have excluded middle is we can't roll this out. So one proves the theorem and one proves the other. What would you say? He said that would be like two violinists playing the same piece in different keys. I'm afraid that is as deep an answer as he had. That is as deep as his theory of the creative subject went.
That may be an example, because I'm again very ignorant about these things, but what do you do when you stumble on that theorem, which apparently says that any function is continuous?
Yeah.
Which apparently Hermann-Weyl at some point said, okay, intuitionism is really exciting and blah, 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 but okay, we can't go on with that. And how many divisions?
There's a couple of sensible...
So how do you, what do you do when you stumble on that?
Well, when Brouwer stumbles on it, he doesn't think he's stumbling, he thinks this is great, and he tries to erect an analysis on it, he can't do it.
Yeah.
Another thing you can do is you can try to find models where it will be true.
Yeah.
And Hiding, Kolmogorov, Kleina, they proceed on this, and then Topos theory captures all of their efforts in a very neat format.
Yeah, but on the side, Kolmogorov proves extraordinary theorems about dynamical systems, which totally contradicts that. I mean, of course, Kolmogorov was a genius, so on the side he could do that in the evening, but he couldn't. Yeah. I mean, he wouldn't take it really seriously.
So one thing is you
It's
just
very serious, but the point is it's not monolithic. Different things are true in different topos.
Yeah.
It's called productive contradiction. Dialectically productive.
Yeah, okay. How do you make it really productive?
So now you try to find which toposes is it true.
Yeah.
Is there... So the sort of zero-level effort is just, what are all the models of this? And it's reasonable to say Topos models because all the sensible models are. What are all the Topos models of this? This is a clear mathematical question. When is this theorem true in a Topos with natural number object? Another question is, which of these toposes have mathematical applications? Are some of these a nice place to study, say, some theorem in integral analysis? Maybe it would be nice to study it in this environment. I mean, this is what happened already in the history of set theory, when they come up with models of CFC where all subsets of the reals are measurable. And they say, boy, the measure theorists will love this because all subsets are measurable. But these are models that you can't work with. You can't live in them. And yet another project is, can we find Topos models that are plausibly connected to Brouwer's philosophical motives?
Just like non-standard analysis, which never took off, really. I mean, from the mathematical viewpoint.
Yeah. So say you look at Kripke models, you say, Kripke models are related to Brouwer's viewpoint, because here the creative subject is advancing, getting more and more facts, including getting contradictory facts on different ones of his lifelines.
Yeah.
Well, I mean, I should have said, but there is a very, very specific point of contact, which is Kripke likely, which says that the topological state, or the locale topos, whatever you would like to call it, as a parameterizer of variation that's sufficient for Brouwer's needs, and also kind of generic for, it's precisely the integers are ordered by divisibility. So that ordered set corresponds to
Yeah.
some kind of zero-dimensional space.
Yeah. So there are mathematical questions you can ask here,
Mhm.
including questions relating to applied math. Is one of these a context good for applied math? And relating to the philosophy. Does some of these contexts reflect what Brouwer might have had in mind? Although, I keep coming back to this, Brouwer did not have very clear ideas in mind.
Yes, I want to make a comment on that. It is not a direct answer on the fact that what do I do when I have all continuous functions, but I want to remark that distribution theory is basically built on what engineers and signal analysts were doing in the beginning of the 19th century. They were
Yeah, but
transforming and deriving functions which definitely are not.
Yeah, but it does not contradict anything.
Well, that's a different approach.
That's completely different.
You make all functions continuous by expanding your notion of function
Yeah.
and weakening your notion of continuous.
Yeah. Yeah. So it's really an expansion of the domain.
Yeah, so that's a different response.
Yeah, that's
and
very
that
different.
one seems to have no philosophic relation to Brouwer, whereas the
No,
Topos
no.
one really does, through these cryptic models, is a kind of a type.
I seem to recall that, Bill, you in your 1973 Bristol colloquium paper actually touched on the example of the Brouwer continuity proof. I mean, precisely as illustrating that although there's no contact at the level of Brouwer's subjective idealist motivation for his creative subject, nonetheless there is a very natural explanation in Topos logic why that condition that the gas and the continuity proof should hold in the right Topos.
There wasn't, I mean, there was nothing esoteric at all, simply a remark that even a cubic polynomial it doesn't satisfy
The cube root, it doesn't.
Cube root.
the cube root. Yeah, there's no.
It won't exist if functions are all continuous.
Yeah. Well, yeah, no doubt.
Yes.
But at what point did Hermann Weyl become disappointed with intuitionism, for instance? I mean, disappointed. It may not be the right word, but
Already by the 1949 edition of, what is it, Mathematics and
Mathematics and the natural sciences.
By the 1949 edition, he's saying, we just can't live without Hilbert's mathematics. Brouwer's motives are lovely, but nobody could live without them.
yeah.
Also, historical question. What is it right that this intuitionistic semantic, topological semantics from intuitionistic logic is Tarski who founded it first, right?
That's a little bit later.
Tarski had thoughts about it.
Scott, I think, is
Well, certainly, I suspect that, yes, I think Tarski in the 30s, and maybe not the first, saw the open intervals on the real line as a model of an intuitionistic sentential logic.
But he made no connection to, say, philosophical motivation.
Well, it's too weak to be very interested in connected because it's just sentential logic. Predicate logic took more, and higher order arithmetic just has no standard intuitionistic form. Like say 438 names.
Yeah.
It's a system for names. It's a phylogenetic system of names. It's not 438 separate names. But
one aspect which what we talked about near the beginning, which I think is worth discussing a bit further, and very interested to get both your and Bill's reactions here, is just how very central the use of choice, or rather the non-use of choice principles continue to be here, because you have motivations, you have this understanding of choice coming from both from the psychology, recognizing that homology typically deals with the conditions of existence of instructions to inverses, whereas obviously the axiom choice holds in the case where you have no instruction at all to the existence of inverses. And there also seems to be a connection there with the homotopy type business that Jean-Pierre was talking about yesterday, because again, the way that he has to think of sets is the homotopy type. Again, it seems very natural that choice should hold in that setting, because, and in the top setting, of course, that's the condition that there should be global sections, the stability of the global section structure. All of these essentially topological geometrical conditions And that kind of naturally seems to be the correct way of thinking about choice and how it should be thought of as the strong indication of absence of cohesion.
It could be. I tried during my sabbatical year. I tried to find precursors of this in Brouwer's topological work, which is all about homotopy, it is all about stability under variation. I tried to find some kinship here. Like I say, what I found was utterly gratuitous use of proof by contradiction, and no visible tie to Brouwer's later thinking. I could not make any connection. I can see objectively how, in terms of Topos logic, I can see how thinking about topological spaces could lead you to this logic. And I kind of want to say that implicitly it did lead Hiding to this logic because he's looking for some way out. But I cannot see a link in Brouwer's thought from his topology to the intuitionism. And it's striking that Brouwer made no such link. Brouwer stopped writing on topology when the intuitionism came up. I think he has some intuitionistic proof of the fixed point theorem, but he basically stopped writing about it. We have testimony on this. All the bright young topologists in Europe wanted to spend time with Brouwer. Menger, Urias, Fluff, they all, and often, Viatoris, often overlapping. They all want to spend time with Brouwer, and they get there and they find a man who will not talk to them about his own work.
Well, I read this quite a
And
lot.
they're forced to talk to each other.
Which is actually much better.
I don't know if it's correct, but I just the suggestion that probably he was still kind of not satisfied by his own proof of fixed point theory, and that was one motivation to look as a more intuitionistic proof.
Yeah. But what he doesn't see is any link between his own thinking. He doesn't look at this and say, oh, you know what I was really thinking here? He doesn't do that. He rather abandons the subject. On that particular one, because it's so famous, he tries a short note, but he basically abandons the subject because he can't connect it to his intuitionistic thinking. He lectured on homology. So far as I know, these notes are lost. Most of this paper is lost.
But my point was actually not, I completely take the point that you made about Brouwer, but in fact this was what I was trying to get at. It's precisely because of the weirdness of Brouwer's conceptual motivation that this does seem to become clear in Brouwer, and that, there is no sense of what the connection is. But what I'm saying is that given the subsequent development of our understanding, in particular of what Bill has been talking about, the understanding of the variations as a kind of special case of cohesion, and the Topos logical being the Topos structure of being the natural way that we have of getting at the geometric and topological information about the structure of the domain and variance variation, limited case of cohesion. We now have a much better way of thinking of why it is that choice and the failure of choice is so central. It does pick out the case of absence of cohesion, constancy relative, or getting steadily closer to something like absolute constancy, which is not the way Brouwer's thinking at all, because
And even that,
he's just thinking about variation in an entirely kind of subjective.
But I think there have been a number of papers and a number of presentations.
If you say that the Heaviside function of the direction rule is quite a contradiction to me. So the only thing
No, because you simply change the meaning of being.
no, they did not change the meaning of being differential.
But you've expanded it, but it's not contradicting anything.
No.
and some of those actually lead to numerical
They
algorithms.
just approached me and then kind of.
And I would go through a very nice talk on it, and then you get into this huge
build on a
problem
model,
of
so
taking
distribution
small
the
steps.
chain
You feel as you're getting
to
closer,
make
you
it
want to take
compatible
small
with
steps to be
mathematics.
accurate.
But
Small steps
Well,
means
not
dividing by
contradict. It
small
did not
numbers,
contradict what people were saying
which
before.
means you
It's
trial
just-
errors.
but it's this is
So yeah, there is
okay.
work on
It's quite
constructivizing
different. I mean,
but
just
what
to
there
get
isn't
another
is
notion.
Brouwer at any
The
point
approach is
saying,
quite
but you
different.
see what my real
Yeah,
thought
the
here
approach
was. My
is
real
not
thought
confusion
was
there,
no,
everything was smooth,
because
Yeah,
he didn't
but
have any real
this
thought.
also contradicts, but it is
No,
ordered in another way.
no.
Yes,
They do not
exactly.
contradict.
It's
It's
precisely
just
my point.
really kind
Whereas,
of notions of
looking at
that's
Topos
something
logic
which
as
before
the
was.
natural logic of variation,
So
which
it's
kind of
okay. I mean, it's
does
not
give
only
us a
okay,
much
it can
better
be very
understanding
useful.
of why choice
So, but you don't see the usefulness of
By the way,
every
not direct.
every function contains.
No, because it flatly contradicts anything that has to do with physics. So
yes.
even remotely.
The idea is that
Yeah.
actually,
And it's
all
just
physics agree about Newton's method.
Uh-huh.
The typical thing was Newton's method around that time. It continues to be so.
Yeah. Yeah.
So it's not just an abstract thing. It's the Newton map that's derived from the given problem, which is typically polynomial of degree minus 1 itself, no matter what problem you start with. So some of them are very
Yeah. Yeah. And that makes sense.
chaos.
Whose article was that?
Jeremy Gray.
Jeremy Gray.
The chapter we talk about on the
Of course, I mean, Brouwer was very indignant against applied mathematics, because applied mathematics is the attempt to impose our will on nature, which is a bad thing. But Brouwer's teachers in Amsterdam were intimately immersed in applied mathematics. It was mostly something taught. It was, so he will certainly be much exposed to that perspective. Even though, given his profound understanding of God, he was not.
Andre?
Could you just elaborate your last 2 points, I think, in the next slide? That category theory is so general that nothing weaker than explicit construction can work a problem for it.
Yeah.
Do you have, like, examples? Could you just specify? And next point also, whether do you mean something that category theory calls seals non-constructivity?
Well, I mean, innumerable theorems of mathematics take the form of showing of the fact that right adjoints preserve products. So the proof that right adjoints preserve products is going to have to apply in algebra and analysis and topology. It's going to have to apply in combinatorics. It's going to have to apply everywhere. So it's going to have to be stable under lots and lots of kinds of stress. And I take constructive logic is somehow stable. You only say something exists if you can name it, if you can say why it exists. You only affirm a disjunction if you have grounds for one or the other. And if you're going to, so any theorem as simple as right adjoints preserve products, which is going to apply over the whole range that that does, is going to have to be constructively provable. This is meant to be a mood and not a precise statement. But, and conceals non-structure. Yeah, so what this is actually declaring an achievement of category theory. It's saying that category theory helps us separate the phases of an argument. We put the complexities in the base, which is inevitably complex because it's very individual. We don't have the complexities in our general tools for dealing with them.
And complexity is non-constructivity. Complexity is not the same thing as non-constructivity. No.
Well, let's say non-constructivity is kind of complexity. The category theory is isolating the general reasoning, which doesn't just say, oh, there's a solution somewhere, go find it. The general reasoning, it really does proceed, so to speak, constructively, that gives you the grounds for a choice, tells you what exists. Almost, because over and over again you are invoking choice among isomorphic candidates.
But I mean, constructivity certainly contemplates an arbitrary complexity in a constructive argument. I mean, it's contemplating using all the electrons in the universe as an example of any idealized definition they might make of constructivity. They always have to contemplate. So it's arbitrarily complex.
Yeah, but that something is going on here. The category theory is partitioning the argument. This is a perspective I've been pushing a lot with some kinds of mathematicians and philosophers lately. Think of, in particular on the cohomology. This cohomological apparatus, this is not a powerful tool that's digging into the arithmetic. This is like a spreadsheet. This is just organizing the information. It's merely organization of stuff that you have to organize somehow. And that's saying, the organization is constructive. The stuff it organizes may or may not be. That's.
And this is not unconnected with the point which came up in the discussion when you were talking about why the contrast between category theory and, say, analysis. that it's just so the kind of reflexes of postulation in the case of category theory is seeing how the diagram just comes so much more naturally to dictate to us. And you made the remark in passing, you made the remark that this is because significant information is typically coming from maps out of the product rather than into.
Yeah.
And that seems to me to be also connected with this, because as you say, typical special cases, what was the remark you made, Bill, about the with respect about the, I mean, Colin picked up on it by saying, yeah, this is because maps are typically, significant information is typically being carried by, information about cases is typically being carried by maps out of the product. I'm trying to remember what the
Runaway maps,
yes, that's right.
Yeah.
That's right.
Yeah.
Well, I mean, this just seems to me to be a very pregnant insight that could be.
And general category theory is precisely not about those ones.
Yeah.
General category theory is about maps into products.
Exactly.
And it's about maps out of products in the Cartesian closed case.
Yeah.
With where
I have a talk called Why Functionals Need Analyzing. Explain why there's a whole subject of functional analysis. It's because you actually have to analyze those functions. Whereas in the space which they're defined, flip of the switch.
Isn't it a bit reductive to reduce cohomology to like bookkeeping? Because after all, I mean, Hilbert or Noether wouldn't like it. You can also say that it was born from resolutions. Namely, you have free objects. You're supposed to understand free objects, free modules. And then there was a brilliant, wonderful idea of Hilbert that you can, maybe not Hilbert, I don't know the exact history, that you can resolve these things into free parts. So it's breaking things into free parts, into free objects, which you're supposed to understand better. Well, syzygies, I mean...
Okay, that's
and resolutions are still the big thing in a way. I mean, in the hands of Courtenay, it leads to derived categories and so on.
Yeah.
So to reduce it to just bookkeeping of the information, where you're actually breaking things into free units which you're supposed to understand by resolving something, it's not quite the same. I mean...
no, it's not the same at all.
No, I mean, it's not just bookkeeping.
The theory of derived functors of an abelian category with injectives is just bookkeeping and will not prove any syzygy theorem. When you apply it to polynomial modules, you can prove syzygy theorems. That's deep math. That's about the modules, not about the derived functors. The derived functors are merely a bookkeeping device for explaining the calculations.
But okay, then I'll make again the comment which you won't like, which is these things were born out of mathematical objects. They were not born out of nowhere. For instance, if you take, you might wonder why, but that's a fact. No, they were all. For instance, if you read now, I mean what you were saying, I mean, what I do like everyday life. If you read Greenfeld. What happens? I mean, you take Maclane's coherence theorem, and then suddenly you have the brilliant idea that you can deform the associativity. But you don't do it in an abstract way. You do it in terms of very complicated mathematical objects, which are profinite quasi-Hopf algebras. Right. And then suddenly you have a whole new world out of that by deforming the associativity, and then you find... like profinite things when and which are connected with the Galois group and the rational and blah blah blah, but that's not never born out of staring at a diagram and saying, I mean, with A being A. No, A is a certain deformation of a quasi-Hopf algebra.
That's great. Yes, you can though talk about deformations in general. You can give the general theory of deformations. This is a sterile bookkeeping theory. When you apply it...
Koncevich and Solomon are writing a book which is extraordinarily complicated, blah, blah, blah.
And it's not applied to particular cases?
In a way, yes, it is. I mean, in a way, yes, it is. I mean, like, for instance, derived algebraic geometry was born only a few years ago because they had moduli problems, again, the Russians, and they wanted to... specific moduli problems, which could not be understood in terms of one stacks or anything. And so it's a very complicated subject, and then you have these moduli problems, and then when you when you're very good, you think about it and you start deriving algebraic geometry.
Yes, and if you didn't apply it to moduli problems, if you just studied the general functorial apparatus, you could do that. You could get general theorem.
But you would never get the idea of studying
Precisely,
it.
and that's my claim.
You would never ever in your life think
Okay, so
the idea of studying anything like that.
So we agree.
I mean, you could never.
Nobody would have invented spreadsheets if people didn't do accounting. You would never have invented spreadsheets
Yeah.
if there weren't companies with complex business needs. But a spreadsheet
Maybe the
is a
exponential.
bare organizing device. The complex situation of one company, which they are able to record on a spreadsheet and thus able to understand better, very complex, very concrete spreadsheets would not exist without it. But spreadsheets are mere organizing devices.
Yeah, but then you're saying that once you've removed all the mathematical objects, then what remains is just very natural and organizing devices,
Yes, that's
which is okay, but
Yes, which is fine. That's what he says.
but it seems to be very disappointing the way if you put it that
Some
way.
people, and this is why they
I mean, to me it's just like, okay, it becomes very natural, but so what?
Yes, and this is exactly a lot of people's response to Grothendieck. All this general stuff, okay, it's great, it's pretty, but so what?
No,
This is
I mean no,
many people's
because
response.
Grothendieck does the same thing as Drinfeld. It starts from
Are you going to
incredibly...
tell me that people don't respond that way?
Yeah, of course,
they
but they
do.
misunderstand that. That's a misunderstanding because, I mean, Grothendieck's work is not about applying category theory, not at all. It's about thinking of certain mathematical objects, which are not really concrete, but okay, reasonably concrete,
Yeah, for example,
reasonably classical.
Little and tau cohomology groups that contain arithmetic information and give deep results in arithmetic.
Hmm.
But how do we get that information out of them? We organize them into a billion categories. We organize them into derived categories.
Sure.
This is all organization. The complexity comes from the groups.
Yeah.
It comes from the arithmetic.
It comes from the
Without
mathematics.
central organisation.
But not only it comes from it, it's suggested by. Never in your life would you, I mean in my life, would you think of étale cohomology were it not for the fact that you wanted to construct the Veil cohomologies with characteristic zero coefficients moreover.
My friend, you have to distinguish in the dialectics of development of where a thing comes from, what it is, what it then gives rise to, and so forth. You have to
Sure,
recognize
sure,
all these steps.
Sure.
Simply by saying, well, this step is not that step, and therefore nothing.
Well, okay, but
This is the response people have to van der Waerden's moderne algebra. They say, oh, these are pretty theorems, but the point is Galois theory. The point is group representations. The point is this actual math. This stuff would not exist. Absolutely true. It would not exist without those applications.
No, or the group representation themselves.
Yeah, and people say, yeah.
We're addressed in that way.
well, maybe I would
That's the point.
I would object to the word application because they're not applications since they suggested the whole thing in the first place.
But they are instances.
Well, yeah, in retrospect, they're applications.
But that's been very undialectically. Because they suggested the thing in the first place, and it was then raised to the level of
Yeah.
articulation and clarity, that made it
Well,
provide
one of the
the
main points is that they
representation.
then have more applications.
Yeah.
But you then have
Well,
applications, exactly.
sometimes,
But let me say
yeah, of course,
quickly.
of course.
If they don't, then...
Yeah,
Let me
if they
say that
don't.
briefly. You say it's in retrospect. Indeed, it's in retrospect. Whose retrospect? Bartel van der Waerden's retrospect. Bartel van der Waerden writes that book by retrospecting on this material.
Sure, yeah.
And that book becomes the correct entry point into these things.
Yeah, well, yeah.
It's an achievement. This separation, separating the levels, is an achievement.
Yeah,
But it does get achieved.
yeah.
Exactly.
It does get achieved.
There's an old joke about these two gentlemen never agreed. They were arguing from opposed premises. But in this case, these two gentlemen will not agree, even though they appear to be arguing from completely shared premises.
Well, we do.
So I think at this point we should move on to the bit there.
I was going to make another comment, rather different, going back to your very, very beginning about how to define constructive and what the Topos have to do with it. I was struck in Provitz's lecture. He gave these 6 axioms of VHK for what is a constructive proof. Well, these axioms are actually theorems in all the local Cartesian closed category models.
Yeah.
Whatever they might be made of. They might be made of Mulry's recursive topos, they might be made of effective topos, of continuity, of eventuality, and so forth. So somehow at the very least, if you're going to assign the label constructivity, it has to be both those kind of axioms, as well as the part of the abstraction stuff out of which it's made.
Yeah.
I think we had, Andre, did you?
No, I just put the same.
Yeah. Any further comments or questions? For sure? It seemed to be going at such a rate of energy. Has everybody finished everything that they want to say, or remark, or contribute? Okay, well in that case we'll draw it to close. Thank Colin and thank the participants in a very, very This is what we all hoped for. And thank you again, Colin, very much indeed. Okay, let's take a short